Oh, how do you know that it must be a delta function here rather than a general function of x? Well, basically, so here I've assumed that it's actually a conformal field theory. Otherwise, there could be a more general function. So this is that instead of QFT, here I'm really speaking of a CFT. And then there is no other thing you can write which would be consistent with conformal invariance. So in principle, if you're studying a genuine quantum field theory which has an RG flow from one fixed point to another, that could be a more complicated object that depends on the scale. But at the fixed point, you can argue that this is the unique allowed form variance. So in principle, you can study an RG flow from one CFT to another. Let's say that you deform the theory by some relevant operator. This CFT would have kappa 1, and this CFT would have kappa 2, and they would change along the RG flow. Okay, so you can actually calculate the difference between the two kappas by writing some nice formula that integrates along the flow. And so this is physical mod, they're both physical mod 1, and the difference can be written in terms of separated point correlation functions, which are manifestly well defined. And so this is just at the conformal fixed point. Otherwise, there may be a non-trivial dependence that interpolates between the two kappas.
And if you are not looking at CFT, then it's a K mod. So let's say
this would still be true.
This would still be true.
And let me now prove this fact. I want to prove that the kappa is observed mod 1, and tools, I'm just going through that because the tools would be important in what comes next. So one central idea that I will use many times in what follows is that when you have such a U1 symmetry, it is natural to couple the theory to an external gauge field which is non-dynamical via this coupling, right? Plus plus Siegel terms. So a mu is a non-dynamical vector field. Non-dynamical gauge field. Okay. A U1 gauge field, non-dynamical U1 gauge field. So it's just an auxiliary object that helps you to bookkeep various correlation functions. Okay. Now, so basic axiom of quantum field theory is that observable quantities are defined modulo counter terms that you can write in terms of background fields. So observables, and this is also true for entanglement entropy, for sphere partition functions, for all the quantities that you will hear about. So observables are defined essentially modulo local polynomials, so local terms, that means that it's a polynomial. Local terms as local terms in the background fields, in all the background fields that exist. Okay. And indeed, for this background field A, we have the following local term, which is just the Chern-Simons term. So I over 4 pi A wedge dA. Okay. So this is a local term that we can write down in terms of background fields, and it generates precisely this delta function in the correlation function of J mu. So correlation functions of J mu are obtained by derivatives with respect to A mu. So if you study the theory as a function of A, you can generate all the correlation functions of J mu by taking derivatives with respect to A mu. So if you take the derivative of that guy with respect to A mu, you find precisely this kind of a local term. Sorry, there is some background noise. Okay. So now this is a very subtle local term to write down. So if you think about it as a counter term, it's a very subtle counter term because it must be properly quantized. We must have that n is an integer. Otherwise, this local term is not gauge invariant, and we're not allowed to use it as a counter term. So observables are defined modulo local terms in background fields, but these local terms must preserve all the symmetries of the theory, and then they parameterize the ambiguities. So this guy is a good local term only if it's properly quantized. Otherwise, it ruins the gauge invariance of the regulator. So it just represents some regulator or some lattice, which is gauge invariant. Okay. So this is why we are allowed to shift kappa by an integer unit, but we're not allowed to shift kappa by a fractional unit. So if two different people calculate kappa in a given conformal field theory using two different regularization schemes, they must differ only by an integer, as long as the two regularization schemes are gauge invariant. So that's the general statement. This is why kappa is unobservable. Every two people who decide to calculate kappa would agree modulo an integer. Okay, so this was just an introduction about Chern-Simons terms in 3 dimensions. Is this agreeable? Okay, now I'll remind you of another topic that will be very important, which is the Cardi formula. Let me maybe erase that and remind you about the Cardi formula.
I'm sorry, the n, because the n is quantized.
Yep.
Well, it's only in another billion B.
This is U1 in U1. Okay.
For U1, it is gauge invariant up to a surface term.
No. So, okay. So the question here was whether it's true that this is quantized even for U1. So the answer is yes. It is quantized even for U1. Well, the simplest way to see that is to put the theory in a torus. So let me explain. So let's take just one-dimensional Chern-Simons term just as an analogy. So then we would write dx a naught on S1. So we can make a large gauge transformation, which would change the action by something which is not integer, if the coefficient of that guy is not integer. Okay. So it is necessarily quantized. Okay, so there is an interesting observable in 3 dimensions, which is defined modulo an integer. In the situation that I will discuss today, it will be a little bit more interesting, because this observable will be defined absolutely, not even modulo an integer. So that's one novelty that we will discuss today, where there is a certain Chern-Simons contact term, but because of the physical context of the problem, this counter term is not allowed. Okay, now I'll remind you about Cardi's formula. And you'll see how all these topics are related to each other. So Cardi's formula is the following fact. You take a 2-dimensional conformal field theory. Okay, it has a bunch of operators with scaling dimensions delta I. So there is a list of scaling dimensions for all the primary operators and all the descendants of the theory. And you can consider the following statistical sum. So you take all the operators, and you just put e to the minus beta times the scaling dimension, and you sum over all the operators in the theory. So that's an interesting, well, it's like a kind of statistical partition function, observable. Parenthetically, I want to comment that this can be derived as the partition function on S1 times S1. Okay, so this object is also the partition function on S1 times S1 that is obtained via radial quantization. But I'll explain a bit more when we go on. So what Cardi has found is that if you take the small beta limit of this object, so this goes when beta becomes very small. So the large beta limit is trivial. It is dominated by the lowest dimensional operators in the theory. But the small beta limit is very complicated because all the operators dominate, and you need to know something about the high dimension operators in the theory to say something intelligent about the high temperature limit of this partition function. So what Cardi found is an exact result, which is something like pi squared times c over 3 beta. Let me just see that I got the coefficients straight.
The partial? Oh, okay.
Okay,
So,
well, let's keep to these coefficients. So this is what Cardi found. So 2 things. One is that the sign here is positive. So when beta goes to 0, there are more and more operators that dominate. And thanks. Okay, yeah, that's correct. So there are more and more operators that dominate, and that's reflected by this fact that the exponential grows. And the other thing that's very interesting is that this thing appears. So pi squared and 3 are familiar, and this is the central charge. So what Carney found is that the structure of the theory at very high dimensions, of the spectrum of operators at very high dimensions, is completely controlled by the central charge of the theory. So the central charge, which appears in the Virasoro algebra, or in the trace anomaly in 2 dimensions that we've just heard about, is responsible for the density of operators at very high dimensions. Okay. So one question that I would like to discuss is whether there is such a formula in 4 dimensions. So in 4-dimensional conformal field theories, we can also make a list of all the operators and all their dimensions, and we can form this kind of statistical sum. And the question is whether it is still true that at very high dimensions, the asymptotic growth of these operators is controlled by some central charge. For example, in a 4-dimensional conformal field theory, as we've just heard this morning, there are central charges A and C, and the question is whether there is an analogous formula. It's not known in general whether there is a useful formula of this sort, but today I will prove that if you look at an appropriate sum of this type for supersymmetric conformal field theories, it is true that there is a formula that is very much similar to that. Okay, so this is what I want to discuss. And the proof will involve Chern-Simons terms in 3 dimensions and a whole bunch of other ideas. Okay, so let's start.
So what is the delta I in the Hardy formula?
Say again?
The delta I.
Delta I?
Right. What is
Delta I are the scaling, are just the dimensions of all the operators. So this is the collection of dimensions of all operators. This is just the collection of all the scaling anomalous dimensions of all the operators in the theory.
And what you're proving is true for superconformal fields in arbitrary dimensions?
So
Or 3 dimensions?
what I'll show today is just for 4-dimensional CFTs.
Okay.
SCFTs. A similar result can be proven for 6-dimensional SCFTs. I don't know if there is a similar result for 3 dimensions and 5 dimensions.
I see.
And I also don't know if there is a similar result for non-supersymmetric theories. It's been a long-standing question. But for supersymmetric theories, I think now it can be understood that there is such a formula. Okay, so let me explain how it works. So, when you have supersymmetry, so suppose you have any kind of generic supersymmetry algebra. So we have Q with Q dagger, which is equal to H, or delta, that we call that delta for future reference. Okay, so if you have a theory with such an algebra, Witten has argued that you can define the following interesting object. You can trace over the Hilbert space of the theory, putting -1 to the f, e to the minus beta delta, and then you can put some, let's say, z to the power mu I, zi to the power mu I. Okay. So you can trace such an object, and you find, and that would be a nice object to study for the following reasons. So this is called the Witten index, and it satisfies a few properties which make it a very nice object to study. So by zi and mu I, what I mean is that the mu I are the charges which commute with Q. Charges which commute with a Q and Q dagger. Okay. So you can insert them in the trace. And zi are some chemical potentials. Sorry, this notation must be confusing. I should have written mu I to the power zi. Okay. Or maybe even better, I'll just write e to the power zi mu I. So the mu I are charges, the zi would be charges, and the mu I would be chemical potentials for these charges. So this object satisfies two properties which make it very interesting. One is that the only states that contribute have delta equals 0. So the states that contribute to this trace, they have delta equals 0. That's very easy to see, because from the algebra you see that if you take a state in the Hilbert space, which has a non-zero delta, then acting with Q cannot produce a vanishing result. So it produces another state with the opposite fermion number, and they cancel each other from this trace, because they have the same delta and they have the same charges, because the charges commute with the Q's, so you can diagonalize them independently. So the states that contribute must have delta equals 0. That's one easy observation about this object. And the other observation, which is a little bit less trivial, is that it's independent of coupling constants. So it's independent of the couplings, of coupling constants. And the reason for that is the following. So there is a picture that explains why this is true. Intuitively, it's kind of obvious, because the number of states that the states that contribute to this index are those that have delta equals 0, and in many cases there will be finitely many of them. So this is just some kind of integer. So an integer cannot depend on coupling constants. But more pictorially, there are states which have this is delta, and these are states which are bosonic, and these are states which are fermionic. So once you act with Q on a bosonic state, you get a fermionic state, and vice versa. So states that have non-zero delta, they come in pairs, but states that that have vanishing delta come possibly without any pair. And so if you just imagine changing the coupling constants continuously, if two guys happen to go to 0 delta as you change the coupling constants, it won't matter, because they will still cancel each other, because there are two of them. And if some guy happens to pair up with some other guy, some bosonic guy happens to pair up with a fermionic guy and go to non-zero delta, they would again do it in pairs, and so it doesn't contribute to the index. So it's independent of coupling constants, and the states that contribute have delta equals 0. So it makes this object very nice to study. And indeed, it has been calculated for very supersymmetric gauge theories in 4 dimensions and 3 dimensions and so on. However, one problem with this object has been, for many years, that it was kind of useless for many supersymmetric gauge theories in 4 dimensions. So in supersymmetric gauge theories in 4 dimensions, this is just a motivation. If you take a SUSY theory in 4D, one of the prominent features that we see in many examples is that it has a moduli space of vacua. So there is a moduli space of a supersymmetric vacua. Okay? So in fact, there are infinitely many supersymmetric vacua, infinitely many solutions to the problem of finding infinitely many states with delta equals 0. And so, historically, the Witten index has been computed in some examples in 4-dimensional supersymmetric gauge theories. But those examples are extremely rare, because they have only finitely many supersymmetric vacua. In many interesting 4-dimensional field theories, such as n equals 4 Yang-Mills theory, or those that appear in Seiberg duality, there is a moduli space of vacua, so there are infinitely many solutions to delta equals 0. And so it's not clear how to count them. It's not clear what this trace means once you have infinitely many states that are continuously contributing to it. So infinitely many solutions to delta equals 0. Okay, so historically the Witten index has played a very important role in some cases, for which it could be evaluated, but many interesting examples were not really studied using the Witten index, just because one couldn't make sense of the Witten index for this example, because there are a continuum infinity of states that contribute to the Witten index. Okay, this problem has been resolved in the last couple of years, so let me explain the resolution. Are there any questions about this historical remark? So this problem has been resolved in the following way in the last couple of years. So not all the facts that I'm going to say now I would be able to prove, and also it's not needed for what I'm going to say, but I'll just summarize some developments over the last couple of years. So the main realization has been that these moduli spaces of vacua, they appear when you study the theory in flat space, let's say in RD or R4. So R4, for example. Okay. So the idea was that perhaps we should study these theories in curved space, and then the moduli space will disappear. The reason for that is that usually when you study theories in curved space, you couple to curvature. So some various bosonic fields, like phi would be some generic bosonic field, they couple to curvature. So the idea has been that perhaps we should study theories like n equals 4 super-Young-Mills or other supersymmetric gauge theories in curved space, and then the moduli space would disappear, and we could reconsider the problem of counting supersymmetric vacua only in curved space.
Well, this sort of what Witten originally did, which is on the torus, which is
Yes, Witten did it on the torus, that's right. But these theories, for example, if you take n equals 4 on the torus, it still have continuum infinity of vacua, and so it wasn't very useful. But now people have realized that you can study these theories on interesting curved spaces, such that curvature, which is absent on the torus,
So
lifts the moduli space.
Sorry, the n equals, for example, on torus, so that just only tell you you're on the wrong manifold, right? Or
N equals 4 of the torus would not have a curvature coupling because the curvature on the torus vanishes.
right.
And so there would be, it would be like a free particle.
Right. So
In the quantum mechanics of a free particle, there are infinitely many ground states and you don't know what to do.
you look at some of the manifold.
Yes, so what I want to explain now is that this problem has been addressed systematically over the last couple of years.
For the supersymmetric on curved spacetime, alpha 0 can be supersymmetrized.
You're asking if this coupling can be supersymmetrized? Yeah, this problem has been studied extremely systematically over the last couple of years, and I could maybe spend like 10 hours explaining the details of how this can be done with lots of results, but I'll just summarize the most important results for you to keep in mind. So suppose you just want to focus on manifolds of the type M3 times R, and the R could be replaced also by S1. For applications, it's interesting to replace it by S1, like in the Cardi formula that we compute on S1 times S1. And you can ask for which choices of M3 we can preserve an interesting subalgebra of superchargers. Okay, this is a completely well-defined question that, in principle, you should be able to solve systematically, and indeed it was solved systematically. So let me just tell you the answer. So not every M3 is admissible. Only a subset of the possible 3 manifolds would give rise to interesting supersymmetric theories. So it turns out that the most general answer, which gives rise to an interesting superalgebra, is when M3 is an S1 fibration over a Riemann surface, over sigma. So you take some Riemann surface, could be some genus G Riemann surface, and you put a circle at every point, and you get some manifold. And so these are called, in the mathematical literature, Seifert manifolds. Seifert manifolds. Okay? So it turns out that if M3 is a Seifert manifold, you can preserve an interesting algebra of supercharges, and you can try to repeat the computation by Witten, only that now it makes sense for interesting theories such as n equals 4 and Seiberg-like QCD theories, and so on and so forth. So an interesting example in this class is, of course, an S1 fibration over S2, which is also known as S3. As you know, S3 can be viewed as an S1 fibration over S2. That's the Hopf fibration. So that's an interesting manifold in this class that I will focus on, even though the discussion is extremely general, and I could extend it to any Seifert manifold. I'll focus on this.
When you say S1 fibration, you mean the metric? You want isometry back in the metric?
Yeah. Okay, so this result for M3 is the culmination of a lot of work. I'm just quoting the result. I don't have time to prove it. Now, which subalgebra is preserved? That's another thing you should know. So it turns out that this class of manifolds preserves exactly 2 supercharges, as we need. So we'll call them Q and Q dagger. Okay, so there are 2 supercharges. For every choice of M3 in this class, there are exactly 2 supercharges. Sometimes there are even 4, but there are at least 2. This is all we need. And they close on some killing vector, which I will call K. The killing vector is basically one can write down a precise formula for K, but I'll just tell you what it is schematically. That's all we need. So K is a linear combination of this S1, so we can call this S1 beta, because this is going to be the thermal circle, and the hop fiber, the S1 fiber. So it's a linear combination of S1 beta plus the S1 fiber. Okay, with some coefficients that one can compute, but it's not important. So the algebra just closes on this translation. It's a linear combination of S1 beta and S1 fiber. Hope this notation is sufficiently clear. It's schematic.
Can the fiber become degenerate?
If the fiber can become degenerate. Let me see if I know of any example where it does. I believe the answer is negative. I believe the answer is no. Okay, so this is a schematic structure of the superalgebra. So you see that there is this family of spaces for which one can define a Witten index. And on these spaces, this problem with the of the continuum of vacua would not be so severe, because usually there would be some curvature coupling, and the curvature coupling would lift the modular space. So for this family of manifolds, we can just take this object and compute it, where now delta is the generator. So we can just study this object literally, where now delta is the generator of S1 translations, the generator of S1 beta translations. So it's not the same thing that appears in the superalgebra, and so this thing would depend on beta, but it's still a Witten index, and it should be viewed like one of the chemical potentials. It should not be. So previously, when I discussed this algebra, it did not depend on beta, but there were many chemical potentials that would have led to some non-trivial dependence of I. Sorry, of mu I, function of mu I. Now in this application, the notation is a little bit confusing, also in the literature, but notice that the object that appears on the right hand side of the algebra is some combination of the S1 translations and the S1 fiber. So this should be viewed just as one of the chemical potentials. Okay, it's just an object that commutes with the Hamiltonian that sits on the right hand side of the SUSY algebra, and so this is the partition functions depend, the indices, the Witten indices depend on the mu I and on beta. So maybe okay, is that clear? Even though there is a small issue, I mean this is a common confusion in the literature, but one should keep in mind that this is not the same as delta. Delta is the generator of S1 beta. Yes?
So does the remaining charges only have to commute with those Q's?
Yes, the remaining charges have to commute with those Q's, and therefore also with K.
So that means we get a larger set than the original Witten index.
In some sense, it's larger than the original Witten index because there is always this guy. There is always at least one S1 isometry that commutes with K in this class of manifolds, so you always have at least one chemical potential. Okay? Is this clear? I hope this is clear, even though there is a small clash with the usual notation for the Witten index, but that's common in the literature. Okay. So why is S3 interesting? I'm going to focus on the case that M3 is S3. That's interesting because the space S3 times R. So this, on the one hand, this is a completely geometric picture, but there is also a combinatorial interpretation for this space. This space is conformally flat, so by conformal transformation, we can bring it to R4, and therefore these indices have using radial quantization, this index, the Witten index that we compute on S3 times R, it has a combinatorial interpretation as counting local operators on R4, which are BTS. So I on S3 times S1 beta. has a geometric interpretation as just the partition function on S3 times S1, but it also has a combinatorial interpretation in terms of the sum over local operators in R4. So it's the sum of all the operators in R4 with minus 1 to the f, and then e to the minus beta, and then their scaling dimension, and their R chart.